In the first video, we started looking at the inverse transform method for generating random variates, and we basically used these U01s, which are uniformly distributed between 0 and 1, and transformed these into the desired distribution by inverting the CDF. And so we looked at the uniform distribution and the exponential distribution. The next distribution that we'll look at is the normal distribution. And we have a slight problem here in that there's no closed form expression for the CDF. And so we still have the same basic structure as we do with all random variables. So we're going to have f of x here, and it goes from 0 to 1, has a shape something like this. And so we'd still like to be able to sample something over here and then do the inversion to get gamma, but without a closed form expression of the CDF, there's no way to do that. So instead, we have to turn to some approximation methods. And there are several different approximation methods used for generating normal random variates, and the one that we're going to use makes use of the central limit theorem. Central limit theorem, H-E-O-R-E-M, central limit theorem, in which one form basically says if we have the sum of independent random variates, the sum is approximately normally distributed under some very general conditions. Basically that we have to have enough of the individual components. And so our z, what we're going to do is we're going to compute z is going to be the sum for I equals 1 to 12 ui minus 6. So essentially we will sample 12 independent ui's, and these ui's are still u01, so each one of these ui is u01, and then we'll add those together and subtract 6. And it turns out that z will be approximately normally distributed with mean 0, oops, not 10, 0, and standard deviation 1. And now that we have our z values, we can use gamma is equal to mu plus sigma z, where mu and sigma are the parameters of the normal distribution that we'd like to sample from, and z is the value that we computed using the 12 independent ui's. So if we look back at our spreadsheet on the page normal, you can see that we did just this. And so in this, for this example, we have a mean or mu of 135, standard deviation sigma of 25. And you can see here in column A through L, we sampled our U01s. Over in column M, we summed the 12 ui's and subtracted 6. So column M represents our z values. And then here in column Q, we used the transform mu plus sigma z to get our actual sampled values. And as we've done before, we will evaluate that by computing the descriptive statistics. So we have a sample mean of 135.36, sample standard deviation of 24.58, and then the histogram is as follows, and we can resample. Again, let me calculate, and again, and again. And so through each one of our observations, each time I hit recalculate, we're creating another sample of 5,000 observations and then evaluating. And again, in the quick and dirty method, our evaluation is just observe this descriptive statistics and then observe the general shape of the distribution. And of course, in this case, it appears that that the data are approximately normally distributed. So if we go back and we can ask ourselves, how does this work? This expression work? Well, again, the central limit theorem gives us this idea, or gives us this fact that if we sum independent random variates, the sum is normally distributed. We chose 12 because we can then force the standard deviation to be 1, because the variance of the z value is going to be 12 times the variance of the individual ui. The variance of the uniform distribution is 1/12. And so we sum up 12, we get a variance of 1, and it's a standard deviation of 1. Since the expected value of ui is 0.5, when we sum 12 of them, the expected value of this part of the expression will be 6. We subtract 6 off and we get 0. And so that's how we end up with the z that we can then transform into the gamma that we want for the given mu and sigma. If we're using Excel, Excel also provides two functions. One is called norm S inverse, norm SINV, which inverts the standard normal distribution. So we could do this same sampling procedure by just using rand inside norm S inverse. And so norm S inverse with rand as the parameter will randomly sample and then do a numeric inversion. Excel also has norm inverse, which lets us specify mu and sigma, whereas norm S inverse simply returns a z value. So if you have Excel, this is quite a bit easier. If you're doing it programmatically, then the central limit theorem method works quite well also. The next distribution that we're interested in is the triangular distribution. Whoops, looks like my tildes didn't come through, so let me add those in. And a triangular distribution is characterized by three parameters: the minimum value A, the maximum value B, and the most likely value C, as shown here. Note that some people in some texts will have these parameters this way, so when you're interpreting, make sure that you remember which one of the three parameters is the most likely value. In our case, it's going to be C. And so we have two different ways to do this. If we have a symmetric triangular distribution, which means if C is exactly in between A and B, we simply sample two U01s, and then we compute Q, which we had called gamma previously, simply as A plus B minus A over 2 times the sum of the two U's. If we don't have a triangular symmetric distribution, then we need to sample our U and then compute beta. So beta is C minus A over B minus A, so I'm going to take this value divided by the entire range. And if my sampled value is less than beta, essentially means I'm on this side, then I'm going to compute T using the square root of beta times U, my sampled value. Otherwise, if it's greater than beta, then I'm going to compute T using 1 minus the square root of 1 minus beta times 1 minus my sampled value. And then once I have T, my observed value is simply A plus B minus A times T. So two different ways to sample from triangular, depending on whether or not the distribution is symmetric. So if we go to our spreadsheet, you can see that we have the values that I have are A of 500, the minimum value, B of 3500, the most likely value, and C of 2000. And here in column A, we have our U values. In column B, we have the T value. And you can see I just embedded my condition for my beta inside the if statement, and then my two ways to compute T, and then I compute Q using the final expression. And so using our standard method, we have our descriptive statistics, our average, standard deviation, and min and max, and then the histogram has the general shape of the triangular distribution. So one thing we can easily do here without having to adjust our bin size is to move our most likely value. So at 2000, we're right here in the middle. Let's say that we move that closer to the right end and make it 3000. And now we see we have a significant left skew in our distribution. So the most likely value is much closer to the maximum value. Similarly, I could make this 1000, and we would have the distribution skewed in the other direction. So you can see the triangular distribution is a fairly flexible distribution. It gives us a lot of, there are lots of different parameters that we could model with a triangular distribution using the different parameter values. The next distribution of interest to us is the log-normal distribution. And if you recall, if we have the case that x is normally distributed with parameters mu and sigma, then y equals e to the x is log-normally distributed, is the relationship. And so, oops, that needs to be a tilde there. And so this is really what we're after. Note, though, that this mu and sigma is not the mean and standard deviation of the observed values. Instead, if we want to generate samples with a known or with a given mean and standard deviation, we have to first solve for those using these two expressions. So that's what we have as mu x and sigma x. And this is the mean and the standard deviation of the underlying normal distribution. So our sampling procedure is to take mu y and sigma y and then compute mu x and sigma x. Then using mu x and sigma x, we will generate our x values, which are normally distributed. So we can use any method that we have to generate these normally distributed random variates, and then we'll use this y equals e to the x to achieve our log normal distribution. So if we go to our spreadsheet, you can see on the log normal page here in cell B1 we have the mean of y, which is our log normal distribution, the standard deviation of y. Then we use those two values to compute. Here's our computation for the mean of x and the standard deviation of x. Now that we have that, we can sample our u using our standard u01 or rand function. And this time, instead of summing 12 u01s and subtracting 6, I'm simply going to use Excel's norm inverse function. And so we're going to use norm inverse of our u to specify the position on the CDF, and B5 and B6, which is the mean and standard deviation of the underlying normal random variate. And so x is normally distributed, and y is then e to the x, and we have our log normal distribution. And so we can change these parameters. If I want to say, let's make this 60, for example, and then standard deviation, we can make the 10, and you can see that the characteristic of the log normal distribution is that it has a central tendency towards 0, and then a larger right tail. So there are a lot of parameters that we'd like to specify for our distribution that have these properties of a central tendency at the lower end and a large tail at the upper end. And so by using this method, we can generate these log normal random variates. I've also included on the presentation for your reference a Matlab script that demonstrates how to generate these log normal random variates programmatically. I'm not going to go through this in detail. If you understand or if you know Matlab, it should be fairly straightforward to read, but you can see here we're doing some parameter definition, and then we're looping through for the number of iterations and generating the random variates and storing them to a vector called data I. And so what we're doing, I basically have two methods to do that. The first one, which is commented out, uses a built-in Matlab function to generate log normal random variates, and the second version, which is not commented out in this version, uses the brute force method, which is the method described in this slide. And then we simply, after we come out of the loop, we do the histogram to plot the data. So again, you can use this Matlab script, and you could easily replace the log normal distribution with any of the other distributions that we've seen. The last thing that we're going to do in this video is look at how to sample values from a discrete empirical distribution. So here is a distribution, and this is a distribution of predicted demand for a new product. So consider your company's making a new product, and you're not sure what the demand is going to be, and so someone in the marketing department has provided you this empirical distribution. So they're essentially saying there's a 10% chance that we'll sell 2,000 units, a 40% chance that we'll sell 4,000 units, a 30% chance that we'll sell 6,000 units, a 15% chance for 8,000 units, and a 5% chance that we will sell 10,000. And so what we'd like to be able to do is sample values from this empirical distribution. And so this is a very straightforward process as long as we do this programmatically. So what we're going to do is we're going to let UI be uniformly distributed between 0 and 1, as we always do. And then we're going to simply evaluate this UI versus these cumulative values. And so we say if UI is less than or equal to 0.1, which is 10%, and we're going to return 2000. Otherwise, if ui is less than or equal to 0.5, which is my 0.1 plus the probability of 4,000, we'll return 4,000. Else, if ui is less than or equal to 80%, 0.8, return 6,000. Else if ui less than or equal to 0.95, return 8,000. Else return 10,000. And so you can see through this function, we just sample this single u01, and then we simply go through the individual discrete values, checking against the cumulative probability at each value, and returning the corresponding value that succeeds in the if condition. And you can also see we can use this general process if we have basically any number of discrete values in our distribution. And so that's all we're going to do for this video and for this module, actually, for quick and dirty random variate generation. As I mentioned earlier in the first video, there's a tremendous amount of information on the general process of generating random variates, both from the perspective of generating the U01s, which we simply glossed over and assumed we had, to generating random variates and then evaluating the quality of the generator and so on. For this module, we're not going to do that, though. We just wanted to go through a couple of quick methods to sample values from several known and popular distributions.